Everyone, in this very video we are going to be looking at laws of thermochemistry, and the first rule here is that the delta H is directly proportional. That means the delta H for the reaction, heat of enthalpy or enthalpy change, is directly proportional to the quantity of a substance that reacts or is produced in a reaction. Okay, and we can explain that with this, that delta H is proportional to the number of moles. Now we see a very good example here. Look at this very reaction. Hydrogen reacting with oxygen giving us H2O. That's actually the reaction for the formation of water. And the enthalpy there is minus 285.8 kilojoules. Okay. Now, but if you notice, look at the second reaction. Both reactions are similar. The only difference is that equation 1 was multiplied by 2. Okay, so if the number of moles of the reactant and product are affected, it will also affect the enthalpy change. Okay, so since we multiply the whole of this equation by 2 to get this second equation, it means that the enthalpy will also be multiplied by 2. So 2 times minus 285.8 kilojoules will give us minus 571.6 kilojoules. That is rule 1. Now, rule 2, the delta H for a reaction is equal in magnitude but opposite to the sign of delta H for the reverse reaction. Okay, I usually like to write it this way, that the delta H of forward reaction is equal to the negative enthalpy of the backward or the reverse reaction. Okay, so when you reverse a reaction, the enthalpy changes. So look at this now. Compare these two equations. You'll notice that both equations are reversed to each other. The product in the first equation are the reactant in the second equation. The reactant in the first equation is the product of the second equation. And can you see their enthalpy? So while the enthalpy for the first reaction is plus 90 plus 7, the enthalpy for the second reaction is minus 90.7. You see that? So whenever the position changes, whenever the reaction is reversed, the enthalpy is also changes sign. Now, this law is commonly applied to phase changes, although it is true when you reverse any thermochemical reaction. Okay, so the phase change when you're converting solid to gas, solid to liquid, liquid to gas, the reverse always changes just the sign of the enthalpy. Now that leads us to the rule number 3. Delta H is independent of the number of steps involved. Okay, this rule is called the Hess law. Now, Hess law states that delta H for a reaction is the same whether it occurs in one step or in a series of steps. Another way to look at this is to remember that delta H is a state property, so it must be independent of the path of reaction. It must be independent of the path of reaction. Okay, so I like to use this example. Let's say you have a reactant A giving you product B in a reaction and the enthalpy is delta H1. Then you have a reactant C giving you a product D and the enthalpy is delta H2. Now if I add it to both reactions, that means left hand side adding left hand side. Sorry, this should be A plus C giving us B plus D. That's a mistake there. Okay, so A plus C, that means left hand side add left hand side, giving us B plus D. That's right hand side adding right hand side. It means that the enthalpy of the new reaction will be summation of the other two enthalpies, and this particular rule is called Hess law. Let's see some questions here. Now the first one says, what amount of heat will be liberated when 5 grams of methane CH4 is reacted with oxygen in the reaction? Okay, so we are interested, we are given 5 grams of methane. Remember from the first law or the first rule of thermochemistry that the enthalpy is directly proportional to the number of moles or directly proportional to the quantity of substance. So when we compare this now, we can see that 1 mole of methane CH4 is going to liberate minus 890 kilojoules of heat. Okay, now 1 mole of methane, since what we are given is mass, 1 mole of methane, if you calculate the molar mass of methane, is going to be 12 plus 4, okay? Hydrogen is 1 times 4, which is 16, okay? So we can say that 16 grams of methane, okay, is going to give us minus 890 kilojoules. That is thermochemically. So 16 grams of methane is going to liberate minus 890 kilojoules. Now, but in the question here, we are given 5 grams. So let's see what 5 grams of methane would do. We can call that X, and we can now make X subject of formula. So by cross multiplication, that means your X now is going to be 5 times minus 819 now divided by 16, okay? And when we do that, we are going to get minus 278.125 minus 278.125 joules as the answer to the question. Okay, so let's go over that again. Okay, we see that 1 mole of methane, 1 mole of CH4, okay, is will liberate minus 890 kilojoules of heat. And 1 mole of CH4 means 16 grams. 16 grams is the molar mass. Okay, will liberate minus 890 kilojoules. Okay, so now we want to know how many kilojoule of heat will be liberated if we use 5 grams of CH4. By cross multiplication, we are going to get 5 times minus 890 divided by 16, okay? And that gives us minus 278.125 kilojoules. Good. We see a question here. It says that if the enthalpy of condensation of water vapor is minus 44.0 kilojoules per mole, okay, what is the enthalpy of vaporization of water at the same temperature? Wow. Now, condensation of water vapor, if we should write the thermochemical reaction for that, it's going to look something like this. H2O. Condensation actually is a process of conversion from gas to liquid. So that means we are going to have vapor, gas, giving us this liquid, okay? So, and the enthalpy here is minus 44.0 kJ per mole, okay? Now, we are asked to find the enthalpy of vaporization. If we should write the thermochemical reaction for vaporization, vaporization is simply the process of change or from liquid to gas. So we are going to have something like this. So we have our water, liquid, now becoming a gas, H2O gas, okay? Now you can notice that the difference between equation 1 and equation 2 is that one is the reverse of the other. And according to the second rule of thermochemistry, if the enthalpy of the first reaction is minus 44.0, it means that the enthalpy of the second reaction will be plus 44.0 kilojoules per mole. I think that's quite easy. Now that leads us to, another question. It says find the enthalpy change for the reaction. We have CS2 plus 3O2 giving us CO2 plus 2SO2, okay? And here we are given the heat of formation of certain reactions, okay? So you'll notice here that according to Hertz's law, we have this reaction. We'll find a way to combine these 3 reactions to give us this. And from what we can see, you notice that if you compare the given reaction here with what we have here for CS2 is in the last equation here. It means that I must have to reverse this equation. Now for this, if you compare this with this, you notice that your SO2, you have your SO2 here. They are both on the same side, but the difference is that I have to multiply this by 2, okay? Now, when you compare the first now, which is CO2 on this other side, they are both on the right hand side, okay? And the number of moles is the same, so that means this will remain same. It will remain same. Now I come again, compare CS2 here and CS2 here. The CS2 here is on the left hand side, and why this is on the right hand side, so I have to reverse, okay? Now when we look at SO2 here is on the right hand side, SO2 is on the right hand side, so no reversing. but the SO2 here is 1 mole, why the one here is 2 moles, so I multiply by 2. That's why we have by 2. Okay, then for the CO2, here is on the right hand side, here is on the right hand side, no change, and 1 mole, no change. Okay, so it means if I want to find the enthalpy of formation of SO2, the total enthalpy now is equal to this, that is the same. I'll write it as minus 393.5. Now plus the second one I have to multiply by 2, so that would be 2 times minus 296.8. Okay, then plus the third one I have to reverse. So reverse means I change the sign of the enthalpy. Since it is 87.9 here, it means it's now going to be minus 87.9. Okay, so if we use our calculator, we can see that the enthalpy of formation is minus 1075 kilojoules per mole. Okay, so that is quite easy. Now let's see another question here. We are given the standard enthalpy of formation of pentane relates to the following. Okay, so you have 5C reacting, 5 carbon reacting with 6 hydrogen, giving us C5H12. Now the standard enthalpy of enthalpy changes of combustion for the three substances in the equation are this: carbon is this, hydrogen is this, and that. Now if we write the equation for combustion, like for carbon, combustion of carbon is C plus O2, okay, giving us CO2, and the enthalpy there is minus 394. Okay, so we see for hydrogen, the combustion for hydrogen should be written like this. Remember, it should be 1 mole, it's kilojoules per mole, so 1 mole of hydrogen, you get H2O. The enthalpy there is delta H equal to minus 286. Okay, now then the third guy there is C5H6, that's pentane. C5H12 plus oxygen is meant to give us CO2 plus water, H2O. Okay, now you'll notice if we balance the equation here, we are going to have that this is 5. Okay, hydrogen, we have 12 here, so hydrogen here would be 6. We write 6 here to make it 12. On the right hand side, the total oxygen here is 10, the total oxygen here is 6, making it 16. So I come here and write 8. So that's the balanced equation, and the enthalpy here is minus 3509. Is minus 3509. Okay, so let's compare this with the original equation. Now the carbon here is multiplied by 5, but on our equations here, the carbon both are on the right hand side, but it means I will need to multiply here by 5. Okay, now the hydrogen here is multiplied by 6 and is on the left hand side. The same thing here, hydrogen here is on the left hand side, but I need to multiply this by 6. Okay, now the pentane here, C5H12, is on the right hand side. Okay, and the pentane here is also on the left hand side. They have 1 mole each, but the difference is that they are on opposite side of the equation, so it means that here I have to reverse. So with this now, we can now find the total enthalpy of this very reaction, and it's going to be, we are going to have minus 394 multiplied by 5. Okay, then plus the next one will be minus 286 multiplied by 6, then plus the other one is reverse. So here we have minus 3509, but the reverse now is going to be plus 3509. Okay, so we can use our calculator to calculate that, and if we do that, we are going to get minus 177 minus 177 kilojoules per mole. Wow, this is interesting. You can throw your questions, you can ask your questions, for further clarification. Please don't forget to click the subscribe button to get notification of our classes. Thank you very much.